Welcome to the 2023 Earth Science Week webinar series based on our theme, Geoscience Innovating for Earth and People. Today we have with us Vitor Coya from the International Raw Materials Observatory to talk about how changes in society are creating a greater demand for critical minerals and the technology being developed to explore mines and automate the process of mining, making it safer and more productive.
Hello, welcome to this talk about the future of mining in Europe and how we are progressing towards invisible mining. My name is Vitor Coya. I serve as Secretary General of the International Raw Materials Observatory. The International Raw Materials Observatory was established in 2017, and as the name says, it observes. Basically, we look to different countries and we try to collect insights on best practice related to raw materials exploration, extraction, processing, and also recycling. And the outline of this presentation basically has two steps. The first one, I'll be talking about the background. So if you want 21st century challenges that we are facing now. On the second part, I'll be talking about the solutions that the European Commission is seeking and how we are progressing basically using research and innovation. And I'd like to start by emphasizing these three drivers of change. I mentioned three because normally this is typically the number of drivers of change that are considered. The first one is technology, and it's perhaps the most obvious one because as we are progressing towards new technologies, we are using more and more elements of the periodic table, and this is what the table or the graph in the topic in the top shows. So from the windmill to the steam engine to the explosion engine and today to renewable energy, we are using more and more elements of the periodic table, and that happens because these elements, they bring properties to the materials being developed that are required by the functions of these technologies. The example that you have on the text tells a story about vanadium being used in the alloys in the Model T by Henry Ford in 1906. So this is the reason why we are using more and more elements when we are looking to new technologies, new functions, new uses. The second driver of change, it's politics. And I've chosen this image in particular because it's a photo of a G7 summit held in 1983 in the USA. The host was President Reagan, and that was a very important summit because it established an agreement on free market principles, meaning that the political situation before 1983 is different from the political situation that we have today, because today we assume that this globalization is more or less, or the liberal order, the liberal trade is more or less common, but it was not like that always. Before 1983, most of these G7 countries, they were also mining countries, meaning that they were extracting the raw materials that their industries were using. Of course, they were facing challenges, not only social challenges. I mean, because Margaret Thatcher, for instance, was facing the opposition from unions. Helmut Kohl in Germany was facing the opposition from environmental groups worried with pollution. And these leaders realized that if they facilitated trade, basically enabling the movement of goods and materials all over the world, then they could also give a chance to developing countries. And in the raw materials sector, this is what happened, because many investors after 1983 started looking abroad to places with interesting geological endowments. And this is the case for Chile, for example, where most of the copper mining started after the 80s. It was developed with external foreign investments, basically facilitated by the free market principles. So that's an important driver of change that we need to have in consideration when we are talking about mining, especially about mining in Europe. The third driver of change, it's also very relevant. And the example that I've chosen was from China. It was what happened with China in the last 20 years, roughly. So China joined the World Trade Organization in 2001. And what happened is that this enabled, again, free trade with China, took millions of people out of poverty, and in less than 20 years, China became the tool shop of the world. Of course, the consequence for us is that it would give us access to cheaper goods because the production costs in China were lower, but it also had an impact on the movement of goods, and especially on the movement of raw materials, critical raw materials and normal raw materials like iron ore, for example. So China became one of the major buyers of metals across the world, and you see all these flows of metals starting to go from producing countries like Australia that were basically before this cession of China to the World Trade Organization, that were exporting to countries like Japan and South Korea. Now they are exporting mainly to China. That's the case for Australia, but it's also the case for Brazil, for example, and for iron ore. So that's a very important driver of change as well. And these, combined with politics and technology, these are the typical three drivers of change, typically considered. But we have a new kid in town. This new driver of change is climate change. And it's new because we never faced it before. I mean, we have historic records how the economy, our society has reacted to changes that were driven by the other factors, but this is new. And it's already having an impact that we cannot basically forget. On the image above, you see what happened in Chile, in the area of Valparaiso, where a reservoir dried up after more than 10 years of drought. And this is already having an impact in mining operations, because we are seeing now that investors, when they are looking to a new mineral deposit, even if the resources that exist are substantial, they are looking to water for the processing activities. And if the water provision is not possible, I mean, even if the project is located in the desert, but if it is located nearby the ocean, then you can have a water desalination plant. But if that's not the case, I mean, if you cannot have access to water, that can basically put your project or put that mining project on hold, meaning that this is already relevant to the industry. Another factor that one must emphasize is that we are not talking only about extraction. We are also talking about processing, and in fact, climate change can affect the entire supply chain. And the image below, it's about news about a heat wave in China in 2022 that basically caused the shutdown of the factories in an entire province, and this was for 6 days, but it could be for 20 days. And I mean, the impact of that is huge, and we never experienced this before. It's difficult to predict, and it's something that apparently it can knock on one's door anytime. So it's something that it's quite difficult to at least at the time being to basically to frame already. But it's important to mention that this factor is already having an impact, not necessarily on the mining sector, despite the examples that I gave, but on policy making. And why? Well, it's having an effect on policy making because policymakers are aware of this concept that was introduced by the Stockholm Resilience Center of planet boundaries. So basically the idea is that we have several systems, several processes that you can monitor to gauge the stability and resilience of the planet, of the Earth as an entity. And what we see now in 2023 is that we are already gone beyond the planetary boundaries in 6 out of the 9 processes that exist. And of course, this is already raising alarm in some areas, especially for some policymakers, not all. But in Europe, this has been taken very seriously. And in the looking to solutions, basically what the European Commission decided already in 2019 was to become climate neutral. So the idea is to make the entire European Union carbon neutral by 2050. And this aim, we now have the Green Deal, but we have a new industrial package. All the idea is to basically push forward and accelerate the energy transition, basically trying to move away from fossil fuels. The problem this brings, remember, to Europeans is that the renewables are far more materials intense than the fossil energy. And since after 1983, we decided to stop mining, or to, in a way, we faced a huge decline in mining in Europe because we were relying on trade. What we realize today is that we are 100% reliant on third countries' imports for many, many minerals. And this is a problem. I mean, it won't be a problem if we were having trade in a level play field, but this is not the case. So we have basically 2 options. Either we look to trade, as we did until now, or we already have concerns because, as I said, some of these materials that we need to import, they are crucial to the economy, and they are being extracted in countries where one can have disruptions. So that's the reason why we are doing these criticality assessments now in Europe every 2 years. So trade is an option. The other option could be the domestic production, meaning that mining again, having domestic mining in Europe. Looking to trade in more detail, I would say that the big problem is resource nationalism. And what you have on these 2 graphs, on the right-hand side, you have the maps, and in red, countries where the resource nationalism is flagged, red flagged, meaning these are countries where resource nationalism is a problem. And I would say there are more countries that are not, at least pictured in red, where resource nationalism already exists, and it can also exist inside Europe. We have seen some countries that are saying that if you want to extract the mineral in this country, you also need to increase the value. I mean, the case for lithium, if you want to extract lithium, you need to have the battery factory also established in this country. And sometimes this is not possible because we are talking about deposits that don't have a dimension that is big enough for that. But that's one aspect of resource nationalism. The other one is political instability. That assessment made in 2022 by Maplecroft, they were saying that out of 120 countries that they assessed, 88 were likely to experience more instability. And probably today, in 2023, one could say that they were fairly conservative, because many countries look to what's happening now in Africa, that were so far reasonably stable, are now facing turmoils. And this is, of course, impacting supply chains, and it's a problem for trade, especially to countries that are relying on imports coming from foreign countries, as it's the case with Europe. So trade has its problems. Of course, one needs to establish, I would say, stable trade partnerships, but it's not an easy task. It's also important to underline that there is competition on trade. For example, China exports a lot of metals and minerals, but they also import. So you see that we are facing competition when we are looking to sources of materials abroad, and the competition can be made by the Chinese, it can be competition between Europeans and the US, it can be competition between Japanese and Australians. So it's happening at the global level. So the other option, the second option that European Commission was looking at was domestic production. And I guess the first question that you might have is, do we have the geological endowment in Europe? And the obvious question, that's an obvious question, and the answer to that obvious question is yes, we do. And I found out this example that I believe it's a good illustration of the European geological endowment. That's a rare earths group that were found for the first time in 1910 in Sweden, in a place called Ytterby, located close to Stockholm. So the Ytterby mine in 1910 was producing basically tungsten, but they also found there these rare earth elements. And it was so important that 4 rare earths were named after the Ytterby mine, where they were found for the first time in 1910. So we do have the geological endowment. But the problem is more complex than most people realize, especially policymakers, because it's not only saying that, okay, we need, for instance, gallium, or we need germanium, so let's mine gallium, or let's mine germanium. This is not the case. Most of these critical raw materials, they are byproducts of major metals, so major mining operations. This is not the case if you look to the diagram in the image. This is not the case for the elements below, like uranium, chromium, lithium, potassium, or tungsten. It's not really the case for rare earths. You can have light or heavy rare earths, but it's the case for most of the other critical raw materials. So if you want to have gallium, you probably need to extract it from zinc or from aluminium. It's a byproduct of the extraction of these elements. If you want to have indium, again, you'll be looking to zinc mining. And if you want to have rhenium, you'll be looking to copper mining. So the situation is complex, and you cannot say that let's have a mine that will be targeting only these critical rare materials, because sometimes you need to have these big mine projects in order to have access to these byproducts. So domestic production has this, if you want, this level of complexity, but it has others. And perhaps the most difficult one is the public opposition to mining. One needs to bear in mind that Europe is a populated continent. I mean, we have a huge population. It's also, despite this political will to speed the energy transition, which, by the way, is supported by most citizens, the reality is that if you need to extract the materials that you need for the energy transition in Europe, you'll be facing a strong public opposition. And these 2 examples are about lithium mining. One is the protests that happened in Lisbon in 2019. People were against mining, lithium mining in Portugal, and we are not talking about lithium mining in some environmental protected area or in a park. No, we are talking about lithium mining in the countryside. And the same thing happened in Belgrade, in Serbia, in 2021. So in Serbia, Rio Tinto had a project that was very well developed, an important mineral deposit that could supply lithium for the European needs. And basically, despite having all the required permits, the environmental impact assessment, everything, once the government announced that they will be giving the mining permit to Rio Tinto, people came to the street, and the protest was so strong they cut off highways, and basically the government was about to collapse. So they backtracked in that decision and they stopped the mining process. So this is something that one needs to take into consideration when we are talking about mining in Europe. So the public opposition to mining in Europe is very, very strong. So the European Commission is basically looking to this and trying to come forward with three, if you want, three different pathways to solve the problem, and they are using European research money to try to find a solution capable of curbing public opposition to mining and basically enabling the domestic production of the critical raw materials that we need. And these are the three solutions: basically reopening old mines, looking to in-place mineral recoveries, some sort of in situ leaching, mining, and going deeper. And just give you a very brief overview of the two projects looking to the first two examples. The first one, reopening old mines. So what you have seen in the image is a robot that was basically developed to map old mines. The idea is that you have this sphere that you can put down below. The sphere will be capable of navigating under the water and basically mapping and sending to the surface the information on the mineral potential of those areas. This is useful because in Europe we have if not hundreds, perhaps thousands even, of abandoned mines that were closed. Some of them were exploited in Roman times, others in the medieval times, but they are closed for centuries. So having this updated information is very important to access the importance and the possible reopening of these mines. That's one solution. Another solution, it's, as I said, in-place mineral recovery. The most typical example is in situ leaching. But this project is looking, that you have in the image named CRM Geothermal, is looking to a different perspective. So in that case, they are looking to the potential of geothermal deposits to provide also metals and to extract, if you want, at the same time. So having a combined extraction of the heat that is used to produce electric energy and also the metals that exist in the solution. We know that these metals exist because if you look to the photo above, it's a 20 centimeters pipe that is basically clogged with scales, with calcium or silica scales, and these scales quite often have metals. So they have metals deposits, typically lithium, also strontium, sometimes gold or silver, and of course iron. So the idea is, can we extract the metals from the reservoirs? In that step we could prevent scaling, so enhancing the energy production, and at the same time cover the EU needs for these raw materials. A quick assessment of that technology showed that it could provide up to 20% of the lithium needs of the European Union. So that can be, it's still under development, but the prospects are, I would say, quite favorable and reasonable. And finally, the reason of this talk and the main topic, it's ultra depths. I'll be talking about a project named RoboMiners that is being funded by the European Commission. So the European Commission allocated 12 million euros to this project. The project is being developed by a consortium that has industry, but also research universities and research institutes. And the concept that was basically at the root of the idea is bio-inspired. So the idea is to have something like a small insect that one could be put underground via a borehole, so a normal borehole. So you could try to put these different parts of that robot, of that bio-inspired robot. They will self-assemble to form this fully functional robot. And the robot will be capable of sensing the mineralized areas, so it will be capable of detecting the ore. And by using their own excavation capabilities, it will be basically excavating these mineralized areas and send to the surface a slurry. And that slurry will be pumped out and will be treated in the surface. And then the robot will be capable of reconfiguring on site, meaning that it will be having a part that will be providing the, let's say, the energy. Another part out will be having the excavation tools and so on. So the reconfiguration will be enabled depending on the needs that the robot will be having on site underground. So that was the concept. What we have now, it's important to say, it's not exactly like that yet. So this is the image of the prototype. It was doing field trips in Estonia. If you go to the website, you can see the movies. They were doing field trips in Estonia 2 months ago, so quite recently. They will be doing more field trips in Slovenia next month. So all these field trials are basically trying to see how the different parts are assembling and how they are moving. As I said, this is not exactly the final product yet. It's important to say that this is a vision to 2050, and in the end vision we'll be having something that will be smaller, perhaps the size of a 2 liters Coca-Cola bottle, with these different components that will be self-assembling and having different functions and working underground. So this is what we have now, but what you see is fairly complex. And it's fairly complex because this robot has these navigation capabilities and also autonomy enabled already, meaning that it is capable of, once it is down below, it's capable of sensing where it is located. So it is using accelerometers, because we won't be having GPS signals or something like that. So the accelerometers, they are very precise. They will be telling us where the robot is located, because the robot will be following a geological model that will be prepared beforehand. So these navigation capabilities are very important. It's also important to emphasize the autonomy, meaning that robot will be capable of even self-repairing, or if you want, self-reconfiguring, using a different model and replacing the models, and of course using energy, especially going to a docking station or something like that to basically to recharge. So all these features are already enabled in that prototype. They already exist. And the prototype has more. So for the navigation, I just mentioned the need of using the accelerometers and also to basically to communicate with the surface. You see how the models in these examples on the left hand side will be basically coupling to each other. So they will be specialized models coupling and decoupling according to needs. And the locomotion use this Archimedes principle. So basically we are using these rods. The equipment in the prototype has 4 rods, and this can be expanded in order to basically create against the walls of the gallery, in order to basically to hang the robot against walls in order to secure it, so we can have the strength to push the arm that will be doing the excavation. So these features are already there. Also important to underline this sensing capacity, because the robot will be excavating. It will be extracting chips, if you want, small rock chips that will be analyzed as they pass inside the robot. So these chips will be analyzed in order to provide the information to the robot if it is really on site. I mean, if it is in a mineralized area. If not, the robot will need to correct according to the geological model, or in case the geological model is wrong, I mean with an important fault, then this will be communicated to the surface in order to do some sort of reassessment. But this sensing, it's very important because, as I said, it will be done in real time as the excavation proceeds. So it will be a combination of geophysical sensors and also mineralogical sensors capable of basically tracking what's going as excavation, what's being extracted as excavation proceeds. The production tool is perhaps one of the most important, because you need to bear in mind that we'll be talking about different contexts. I mean, different rocks, different ore types, different ore bodies, having different features. Meaning the one that is now on the robot prototype is a trichon drill bit like the one on the image, but we have been looking to different alternatives, namely to microblasting and to hydrodemolition. So this is not closed. For the time being, the prototype will be having this arm using a trichon. The advantage of having the arm is that it can allocate more time to areas where it's more difficult to excavate. It might be also possible to combine hydrodemolition and trichon drill bit. So this is still under development. And the production tool is something that is a challenge, because, as you know, in drilling, in normal diamond drilling, one can replace the drill bit easily. In this case, that will be a challenge because it will be an underground robot designed to work non-stop for several days. So we need to find a solution that is sufficiently stable. And I'd like to emphasize the impact of this technology. What we have now with the figures that we have from the prototype, if you look to the production capability, they are very modest. We are talking about half a ton hour, perhaps 0.2 cubic meters per hour. The pumping capability for the pumping out the slurry is also limited. And the excavation capability, it's, as I said, limited by the hardness of the rock. But if you look to the potential, because on the left side what you have it's a map of mineral deposits in Europe, and you remember me saying that that Europe has a very important geological endowment. The problem we have is that sometimes the mineral deposits, they are small. I mean, they can be rich, but they are not big enough in order to use conventional mining technologies and to make mining feasible. But to this sort of technology, a small deposit can be exploited, and it basically changes the landscape. On the right hand side you have an image showing abandoned mines that were mapped in some European countries, not all European countries. You see some countries don't have information, but you see that we also have many abandoned mines where basically one could put a robot and start doing the exploitation in, if not tomorrow, the day after, so quite quickly. So this is an important impact of this technology. And if I may, I would like also to underline two different aspects. One, so by having this sort of robot, we can go deeper, and that solves the problem of geothermal gradient, for instance, that you have in mines like the one that is depicted on the right hand side. That's the Mponeng in South Africa. These guys are working at 3 kilometers depth, meaning that the heat in the rock walls, it might be around 50 degrees Celsius. This is huge. I mean, it's almost unbearable, and that calls for important cooling and ventilation systems. So with a robot, you won't need that. On the left hand you have the Avik diamond mine in Canada, and this is a remote area. Again, with this technology you can mine in remote areas, or, as is the case in Europe, you can mine silently even in very populated areas. I mean, you can have not one robot, because as you see, one robot might not be so, from the economic perspective and from the amount of materials produced, it might not be so relevant, but you can have a swarm of robots. So imagine a swarm of robots mining down below a big city like Paris or Berlin, and they could be extracting the minerals there, and this will be a completely invisible mining operation. So this is the sort of features, or the sort of futures that this technology might put forward. Finally, let me emphasize the environmental footprint. If we were together in a room, I probably at this moment in time will be asking the audience if you have been inside a Roman mine or inside a medieval mine, and asking you to raise your hands. As this is not the case, because this is a remote presentation, just let me emphasize this. If you visit one of these mines, you will notice that you probably will need to enter crawling, because the access and the galleries, they are very small. And the reason why is that the Romans, they were using children. So they were using child labor, slaves, children to work underground. This is not something that was made only by the Romans. In coal mining in the UK for the Industrial Revolution, the British were also using children in the coal mines, and the reason why, it was basically to minimize the amount of rock to extract, of waste rock. So by extracting less rock, it basically minimized the amount of effort to be made. I would say that with this technology, by basically using a system that goes only to the mineralized areas and avoids the extraction of waste rock, the environmental footprint will be much smaller, because we won't have this huge amount of waste rock on the surface. So that's a very important issue to underline. And if I may, to close, I'd like to give you these 5 takeaways for a new paradigm. Remember, I'm not talking about 2025, I'm talking about 2050. So on a roughly 25 years horizon. So what we expect to have in this time frame is something that, using robotic technology, will be virtually making mines invisible. And I believe this is probably the most important feature, the most important outcome of this paradigm. What you have on the red side, so no personal mine, minimizing the groundworks, and of course that also minimizes the capital costs for the initial investment. No dewatering, and of course you don't need to pump out huge amounts of water from the mine, with all the environmental impacts and costs that this have, and of course less waste. So this new paradigm, we do believe that it might be enabled in a few years, thanks to these European Union research and innovation funds. So to close, I'd like to call your attention to a publication that is made every 2 weeks, named World Barometer. This is available through our website. You can subscribe it, it's for free. And that's a collage of news coming from different areas. And I would say that what's relevant is it's not only news about mining. We are looking to news coming from business, from science, from environment, from technology, all these areas that can have an impact on the mining industry, on the mining sector, on the way we are now doing mining. So thank you so much for your time, thank you for your attention, and I look forward to receiving your feedback and your questions. Thank you.
Thank you so much, Vitor, for that presentation. So he is now here with us live, and we are able to ask some questions. If you have any questions, please put them into the chat, and I will ask them out loud so that everyone can hear the answers. But just to get us started, I was wondering, what are some key innovations and technologies that make the RoboMiners robot miner more environmentally friendly and economically viable compared to traditional mining methods?
Oh, thanks, Lindsay. I guess this is the big question. Well, as I said, I believe the paradigm change here will be the size, because by enabling a technology that will be putting down below a sort of tunneling machine that will be sending to the surface the minerals, uh, and that will be targeting the mineralized areas only. That means that we won't be having tailings, we won't be having rock waste piles. We won't be spending as much energy as we do today, because a modern mine is, if you want, is projected. It is designed on man size. So the equipment, all these things are aligned with the need of having humans down below. If you don't need that, then it will be a step change. So it will change the environmental impact, and of course some of the features of the robot, like real time data analysis, all the things that are organized for reducing human exposure, etc. These are also important, but it's the size, the one that is changing. The if you want it, changing the game, and this is not new. As I said in the examples, if you look to coal mining or to Roman mines, it was already there. I mean, the smaller, the easier. And in our case, in modern days, it's not because we need to minimize the drilling efforts. It's also because we need to minimize the waste that is produced.
Right, that makes sense. So that relates to a question that just came up in the chat about the length of the robot shown in the last video, but just in general, how large are some of these robots?
Well, that's a problem that we have still. So the prototype that we have is almost 2 meters long. I mean, in the width is not as much. It's roughly 60, 70 meters, less than that, 60 centimeters width, but it's 2 meters long. And 2 meters long is bigger than what we envisaged at the beginning. But again, this is work in progress. And the aim is to came forward with something that will be, as I said, having the size of 2-liter Coca-Cola bottles, and having specialized functions. So you'll be having that area that has locomotion with the screw, with the Archimedes screw, basically providing the features to move. But you'll be having a different tool that will be specialized in drilling. We will have another one that will be in the middle, doing part of the pre-processing before sending the rock chips to the surface. So all these things, probably you will come up with a sort of assembly of several Coca-Cola bottles. But again, this is much smaller than man size and comparable, and that will make a big difference.
Great. So there's another question that just came up in the chat, that do the cuttings go to the surface in some kind of hose or tube, or won't you need a large water flow to keep the solids moving without clogging the system?
It will be a house, and I believe this is something that it's still a challenge. I would say it's again work in progress, because if you think on a mine, in a modern mine, and the way it is developed, you'll be having a shaft or some sort of access down below, and then you'll be having several galleries. In our case, if you need to have a hose that will be sending to the surface the rock chips, the mine design needs to be different. Meaning that you need to have a mine design where the robot will be having always this tail, this connection, this hose connected to the surface. Perhaps we'll need to have some sort of intermediate chambers to if you want to, that will be working as a sort of storage areas, where we'll be then taking from those storage areas from the surface the rock chips. Nevertheless, we'll need to have at the surface a processing capacity. But again, we won't having the noise. We won't be having all the again the environmental and also the visual impacts. All these things will be absent. So, and they don't need to be exactly on the site. I mean, it can be kilometers away. And again, this is a huge difference, especially if you are considering again the European landscape with many cities, or with many environmental protected areas. So this again can change the game.
Right, fantastic. Another question that came up, what types of geologic settings or deposit types do you feel this equipment or process would be most appropriate for?
It's a very good question. So at the time being, we are looking to three types of, if you want, of geological environments. One is the Cooper Schiefer. The Cooper Schiefer is a deposit that exists across Europe um, with with a sediment-controlled mineralization of copper, um, meaning that it is tabular and it is quite extensive. In some areas, it has 1 meter width. In other areas, it has only 60 centimeters. Sometimes it disappears and it comes up. So this is the sort of deposit that we are looking at because it's quite easy to follow. It has been mined in several places, so it has been cross-cut in several places, so it won't be difficult to introduce the robot there. Other cases are stockwork deposits. I mean, that's the case for um, base metal mines, and then we can put robot in some of these cases. Even today, in still active mines, there are areas of the mine where it's not economically feasible to go there just to extract a small portion of the deposit. This is something that the robot can do. I mean, it's again a very small gallery, meaning it's not so demanding, not so expensive, and it can extract completely all these areas that have potential. Nevertheless, the field trials, I said in the presentation field trips, but I meant field trials that we have been doing. They have been active in softer rock environments, so in phosphate mines. One in Slovenia, the other one in Estonia, and these, I would say, these are the low-hanging fruits. So this is the sort of things that the technology can do already tomorrow. And some of these phosphate mines, of course, they also have critical raw materials as byproducts. That's the reason why we were looking to them.
So is that one of the issues that you've already run into, is that the possibility that there might need to be different robots for different geologic settings, depending on the hardness of the rock or type of rock?
Not necessarily different robots, but different parts of the robot. Meaning that
Appendages.
exactly. So you'll be having probably the same locomotion system with these Archimedes screws. Might having the same features for self-awareness, for the detection of the minerals, real-time detection of the minerals that you are extracting, but the production tool will need to be adapted to the specifics of the deposit. And this is a huge challenge because I mean, people working in the industry know if you need to change a diamond bit every 2 hours or every 7 hours, I mean, that's almost impossible. So you need to have something that is quite stable, quite robust in order to have the robot working without stopping for many, many hours.
That makes sense.
Okay.
The next chat asks about how affordable will this equipment be, and is it possible to mine or drill at any desired angle?
Yes, the second part, yes. So it can go upwards, it can go downwards, because it will be having, again, those screws basically fixing the robot against the walls, and there are no limitations on that. On the price, for the time being, it's very expensive. So we already spent in that prototype 7 million euros. If you sell just one unit, it will be 1 unit per 7 million euros, so it's quite expensive. But we do believe that this price can be down even below 1 million as soon as we started having some sort of dimension, I mean, production capabilities. So this is quite normal in these sort of developments. And if you have several robots that will cost less than 1 million, then again, that changes the economics of mining.
And I'm guessing once you scale down the size, that will also affect the affordability of it.
Of course, it's also important to say that with a smaller size, you might have less production because for the time being, you have like, um, uh, let's say, half ton per hour. With a smaller robot, you'll be having less. But again, it depends on the mineral deposit. If you are targeting very specific tabular layers with high mineralizations, that can happen, for instance, for tungsten, again, it changes. You don't need to have huge amounts of material dig out. So I won't say this is really the solution for iron ore deposits, but it might be a better solution for gold mining, for tungsten mining, for some specific materials that you are targeting in these sort of deposits.
And to go back to the question about the robots being able to move at any angle, is it based on their detection of the mineral concentration? Like, can they change their own angle, or is that something that would have to be controlled?
Well, yes. So they will be having self-awareness, self-positioning, and also artificial intelligence to decide what to do. So they will be autonomous. The idea is that they will be, let's say, monitored from the surface, but they will be autonomous. One of so the robot will be having a curve ratio, so it cannot really, so it will need to adapt or to go beyond and start drilling in a different direction. So there are limitations that, again, are physical and depend on the size of the robot. But the idea is that this technology basically will enable us to have the capacity to follow, if you want, like a dog, to follow the trail, meaning that it will be following the mineralization and it will be reassembling, or readjusting to maximize the amount of mineral that you are extracting. Again, on doing real-time monitoring, doing this real-time measurements. This is something that you can do it on the laboratory, but in modern mining, it's not common. Normally, what we do is that you blast and then you map, you blast and you map. In this case, it will be different.
Okay, well, related to that, is there a possibility of the robot then getting stuck in a mine, or would it be able to get itself out?
Yes, that's a possibility. I would say there is so much money involved that this will be really a problem. And it can be some sort of malfunction. So it can happen. The idea is to have all the critical process, they will be redundant. So we'll be having 3 or different redundancy loops in order to prevent that from happening. But it can happen. You can lose the robot, and of course that will be a huge loss. Of course, at the time being, we don't face that risk because now we have been testing in open pit mines, and the Mexica, the coming trial, it will be in an underground mine, but with access to humans. But as soon as you, let's say, in a working environment, in an operational environment, this is a risk, and we hope to have the tools in place that will enable us to recover the robot. With something more sophisticated than just pulling the house.
So is there an operational depth at this time? So is there a certain depth where it no longer would be able to communicate with the surface or wouldn't work?
No, communications with the surface are not a problem. Remember, you'll be having always the need to have the house to take out the materials, meaning that we'll be having always communication with the robot. To know exactly where it is, we'll be having these accelerometers, which is, in fact, it's a technology that was used before 5G. Remember, when already in the Cold War, all these nuclear missiles that were being developed, they were using the same sort of technology to know, or the planes, to know exactly where they were, depending on these accelerometers. So this is quite sensitive. It works very well. That won't be a problem. I guess that sorry, Lindsay, I just forgot. You would ask me about?
Is there a certain depth that the
the depth? Yes, I forgot about that. No, there are no limitations on the depth. We might have limitations on the temperature, but not on the depth, meaning that it can work up to 70, 80 degrees without any problem. If you have higher geothermal gradient, meaning that if you go to depths of 3 to 4 kilometers in an area with higher geothermal gradient, it was not designed to survive to more than 100 degrees Celsius. And it's already boiling there. Huh?
Right. Fantastic. So another question that came up, do you visualize a swarm of excavation machines akin to swarms of drones?
Well, I would say that yes, this is the sort of feature of future that I do visualize. So, like having this army of if you want, a swarm of like ants, basically going to the mineralized areas and just collecting. I believe this will be it will be the direction that the technology is now taking, and that's again because mainly of public opposition to mining. So all these efforts is to make mining invisible or virtually invisible. So it will be like one hand colony. It will be down below, you don't know it's there, and you just receive the minerals on the surface.
Right. I guess that's ideal. Yeah.
Hopefully, yes, but there are many challenges. Yes.
Right. There's another question that came up in the chat referencing work in the Netherlands on a self-propelling small bore drilling device called the Brilliant Mole. Are you familiar with this work?
No, but I like the name because it's basically what inspires us.
Right.
But no, I'm not inspired. I'm not aware of that.
All right. And then we also had a link put in the chat for the World Barometer from Intra. If you could just check that at some point to make sure that that is the correct one, so everyone has access to that, that would be great. And I guess we have time for one more question. So are there any case studies or pilot programs where these innovations you've been talking about have been successfully implemented?
No, I mean, our trials are the first. We, together with the field trials, we are also doing assessments on the economics, assessments on the technological issues. And so far, and again, these are bench assessments, so they tend to be quite theoretical, but applied to real cases. So we are taking all the information from real operating mines, and all the information that we have is, yes, this is feasible. Yes, this can be implemented quite fast. But again, the field trials only happened in two situations with this prototype. The next steps, I guess, it will be to enabling the prototype in order to have it in smaller sizes, and perhaps working on the production tool, because I believe the production tool is key in order to face different geological environments, different deposits, but also into coming into something that will require a sort of effort on material development, something that will be quite robust. And again, we need to test issues like, can we work with hydro demolition? Can we do? Some people was also considering microblasting. So all these things are still on the table. So what we have now is, I would say, it's the most basic solution, which is the trick-on bit, but it won't be for sure the final solution, because we know that from the current technology that this is not, I would say, strong and reliable enough.
Right. As you said, it'll probably take about 25 years or so to fully develop these technologies.
Yes. The good news is that the European Union already launched a call to follow up for this project. So we hope to continue the work for the next 3 years. And I'm sure that end of this year plus 3 years, meaning in 4 years from today, we'll be having something that will be really much more sophisticated and already working. So it won't be RoboMiners 1, it will be already RoboMiners 2 or 3, and it will be attracting a lot of attention. And again, this is a game changer.
Well, thank you so much for your presentation today and answering all of our questions. It's fascinating work, and we love to hear about it. And we'd probably love to hear an update in the future on how it's going. If anyone in the audience has any additional questions that they would like to ask, we would like you to email us at webinars@americangeosciences.org, and we will forward your questions. And then also, we will be posting today's webinar, as well as the rest of the webinars from this series, on our website within the next week, and there is the link for that. So again, thank you so much for attending, and Vitor, thank you for your presentation.
And Lindsay, if I may, just let me say that, yes, the link to the World Barometer that is on the chat is the right one. I just checked it. everyone is welcome to go there to subscribe in order to have these news, and of course to let's say follow the next developments of robo miners. Thank you also to you and to AGI for inviting me to be here. It was a real pleasure.